Good to be here with you. We were talking with Tom and Sadie about coming here this weekend, and one of the things that I expected was that we might have a chance to cool off, but like you mentioned, it's been warm here. The last 3 daily highs at home have been 86 or less, so we weren't expecting the warm welcome, but we're glad for what we've got. And it's been a really good experience to see the area again. We've been here before. We were down in the Trout Creek area, got to meet some of you there a few years ago, and it's really good to be back again. Like was mentioned, we come from Montezuma, Georgia, and I'm blessed to have the family here. Thank you for inviting all of us to come as a family. It's really nice. We appreciate that. And we are from the Montezuma Mennonite Church there. It was started back in 1953, and I don't usually always talk about myself at the beginning, but you do deserve to know who we are, having invited us to come and be your speaker here. And so we come from Montezuma there. The community was started in 1953. There was a number of brothers that moved down there from Virginia Beach, Virginia, and they were Yoders. So there's a lot of Yoders there. We're some of the Yoders, and it's been a good experience there for us, but apparently, based on what some people say, it's good when we leave too. They say when the Yoders leave town, the county is deodorized. So I guess it's good when we leave too. So we have down there in Montezuma, we have a view of the night sky, and it just doesn't quite match up to what you have here. I was outside last night looking up, and I was seeing stars dimmer than what I've seen before with the naked eye, because your sky is so dark here, and you can see far out into the universe, farther than what we can in Montezuma. So I hope you enjoy your night skies when you see them. God made the heavens. We all know that. But he said that in the Bible it says that he made them for a specific reason, and that is to declare the glory of God. And that's what we've heard already this evening. The heavens declare the glory of God. So there's a specific reason for them to be made, and it's also for times and seasons and days and years. That's for our benefit, and it's to declare the glory of God. And there's one verse that I'd like to look at before we launch into this, and that is in Psalm 89:5. It says, "And the heavens shall praise thy wonders, O Lord, thy faithfulness also in the congregation of the saints." It's kind of like a prophecy for this evening. We have a congregation here this evening of the saints, I'm assuming. It looks like it. So we have the saints here, and the heavens are about to give us a message. Because of what God has done through the heavens, he gives us a message to the congregation of the saints in this way this evening. As a little bit more of a background, I've had an interest in astronomy ever since I was real young. And I have, since then, I've gotten some telescopes, and I've done some study, some research, some astrophotography, and have found things that are really interesting to me and relevant to us as Christians. And I'd like to look at this evening here in the first session, I'd like to see how these things kind of mesh with what the Bible tells us. And then in the second part of the evening session here, we want to take a look at kind of the nature of some of these objects, the sizes of the planets and stars, and their believed, how astronomers believe how far they are from us, the distances from us. So we'll go ahead with that now, and maybe if we could have some of the lights turned off, it would be a little easier to see what we have on the screens. We're starting off here with Psalm 19:1, where it says, "The heavens declare the glory of God." So it's telling us a message about him. And like was mentioned, it transcends language barriers. So this means that when we look at the heavens and we see this view, then we are seeing a message from God speaking it to us in our own language. When we're here in Montana, it might speak to us in English or Pennsylvania Dutch. When someone's in China, it might speak to them in Mandarin, or in Africa, it might speak to them in Swahili. But it's a universal language. We look up, we see the vast expanse of the universe, and it leaves us feeling like we're such a small thing, such a small part of what God has made. It makes it feel like we're lost in the middle of nowhere, yet surrounded by everything at once. The stars are so far away from us, they completely destroy our depth perception. So it leaves us feeling like we just don't know the scales of those things out there. So God speaks to us through those things. And what you see on the screen here now is a sampling of some of the images from outer space. They're all made up of real images. So for that reason, I'll put an R on the screen. When you see the R logo, you know you're looking at real images. This, of course, is a composite of a number of different images put together in one. So basically, this is what happened here. I took a picture of Saturn, Neptune, the Omega Nebula, the Orion Nebula, and the Carina Nebula, and put them all together into one. And so you can see what we have here on this image is not a specific region of space that you could see in one view with a telescope, but it's made up of different objects and different regions of space that we brought together into one. So these are real pictures. As we go through this evening and this weekend, if you see the R logo, you know you're looking at a real image. Now, of course, we want to start at the beginning. In the beginning, God created heaven and the earth. And this is the first verse, the first phrase of the Bible. And it has been under attack by unbelieving philosophers and scientists throughout history. People that don't believe in God have a major problem with what they see in western Montana and in other parts of the world, in all the universe. There's these huge mountains. There's this vast starry sky. So how did it all come into existence? What brought it here? And the answer to that question is so difficult if we don't have a God to answer that question, that throughout history, man has simply sidestepped the question and said, well, we don't really need to have something to bring into existence. If it has always existed, then if it's always existed, we don't need something to start it or to begin it or a creator. So the answer to the question for years has been that the universe is basically eternal. It's kind of like a God in itself. Why do we need to have a beginning for the universe? Well, there's some problems with that thought. And some of those problems started showing up when astronomers were looking at the Helix Nebula, like this right here on the screen, other planetary nebulas, other things all across the universe. They noticed that it looked like these things that were out there in the universe have a finite age, and they were set in motion sometime in the relatively recent past. So what's happening here with this picture that you see is a star right here in the center. You can see it here. Has exploded. It hasn't completely obliterated itself, but it puffed off this shell of hydrogen and helium gases and some other gases as well, and they're expanding away from the star, so it's this beautiful halo of gases expanding out from it. And this star is losing its fuel. And so as time goes on, it's burning up more and more fuel. Thank you. And so that means that it has a limited supply of fuel. It has a finite size, so it can't just keep burning forever. So if it would have existed for an infinite amount of time in the past with only a finite gas tank, then it would have burned out by now, and we wouldn't see it today. All the stars, if they would have been existing for an infinite amount of time in the past, would have all burned out by now, and the universe would have experienced what's called a heat death, where all heat dissipates across the universe, spreads out, heat is lost, and the universe would be about 459 degrees below 0 Fahrenheit today, if that were the case. That's absolute zero. But of course, we have the universe full of light and heat, so that means that sometime in the relatively recent past, these things were actually started, and there was a beginning. So, to make a long story short, astronomers, secular astronomers, years ago, they postulated a new theory, one that was in competition with the steady-state theory, and the steady-state theory postulated the universe just always existed for an infinite amount of time in the past. But today, most people believe something else, and that is that there was a beginning. And so they're conceding that the very first phrase in the Bible is actually true, but they stop right here because this is a difficult word to accept, because all that it entails for my life and for the lives of everyone. There's a moral accountability if a personal God has actually created us. So there was a new theory, and it's a step in the right direction, and it can be summarized into this, the Big Bang Theory. the belief that there was nothing and nothing happened to nothing, and then nothing magically exploded for no reason, creating everything, and then a bunch of everything magically rearranged itself for no reason whatsoever into self-replicating bits, which then turned into dinosaurs and you and me. And so at face value, the Big Bang Theory really doesn't tell us a whole lot. In fact, there's basically nothing there. When you look at all the nothings that the theory starts off with. There's a funny thing about the Big Bang Theory, and that is that even though it's supposed to explain the origin of the universe, that's the one thing it doesn't do. If you study the Big Bang Theory, you'll see that it's a highly detailed account of how that matter and energy could have assembled into the patterns we see today after they all appeared. So the Big Bang Theory starts with all the total sum of all the energy and matter in the universe that we have today. All the material that we have today was there, and then the Big Bang Theory actually starts. So we know that without God, we have issues like this where we just simply can't understand, can't explain things. There was actually just right after the Big Bang Theory, there was also another a problem that, or excuse me, just right after the supposed Big Bang, there was another problem that showed up. It was called the horizon problem, and that is where that it appears to be that the universe just doesn't match with what the Big Bang Theory says that we should see. And it's such an enormous problem that the only solution for it has been a postulated inflation theory. So there's no evidence for it, but astronomers propose that the universe actually started expanding after the Big Bang and then underwent a much more abrupt and high-speed expansion where it expanded 10 to the 78th times in size. So that's 1 followed by 78 zeros. That many times bigger in size in less than 1/quintillionth of a second. And then reverted back to its original Big Bang expansion rate. And that was just plugged in to make the Big Bang Theory work. So the point is that regardless of what we do or try to do to explain a universe without God, it simply won't work. We can't have things just making themselves and assembling themselves. We rely on our own wisdom sometimes to try to decipher these things, but we fall short. And this here can kind of illustrate it. This is a test here. The question is, which square is darker? Is it A or B? And I think it's pretty obvious here. It looks like A is much darker than B, so I'll just answer it for you. But what I'll do next here is build a bridge between the two. And now that I've done that, you can see that there's no change in shade as you go across the bridge from B to A. And there's no gradient there either. It doesn't get darker as you leave B and go to A. It's just the cylinder with its shadow and the other things around here give us the impression that, that one is darker than the other. So we're being influenced by those other things around it. If I take away those other things, then you can see that it's all the same shade. But if we back out of it, then we're back to the first illusion where it looks like A is darker than B. This here is just an illustration of how that we can't even, we can't depend on our own mental faculties to give us proper interpretations of things at all times. And then the God of this world capitalizes on this, and he clouds our vision to make things even worse. And he leads us astray and has caused so many men to believe that the universe could make itself without God. So what we want to do next is take a look at what the Bible has to say about astronomy. Job chapter 9, verses 8 through 10 says, which alone spreadeth out the heavens and treadeth upon the waves of the sea. It's talking about spreading there. And then in verse 9 it says, which maketh Arcturus, Orion, and Pleiades, and the chambers of the south. These are stars and groups of stars that we still call by the same name today, at least these first three. And then it says, which doeth great things past finding out, yea, and wonders without number. So God is doing these things beyond our ability to comprehend and even discover, and they're wonders without number. So it's beyond our ability to count. And there are so many stars in the universe that there's no way we could count them all. We can't even count all the galaxies that hold the stars. There is a creation astronomer, I can't remember his name anymore, that has given us an interesting analogy to help us understand how many stars are out in the universe and believed to be in the observable universe. And the number is so big that we really can't comprehend it. It wouldn't do me any good, or it wouldn't do any of us any good for me to actually say the number, because it's far beyond our comprehension. But what we could do is imagine counting to that number at the rate of speed that our fastest personal computers have. A lot of our computers have 4 cores running at 2.5 gigahertz or something like that. And so theoretically, we could maybe get about 10 billion calculations in per second. So if we could count 10 billion stars per second, we could start it now, and we could wait and see how long it would take us to get to that number of stars that's believed to be within the observable universe. Now, we don't know for sure, but what astronomers have done is they've taken a telescope and they've looked at a small segment of space out here, and they've counted the galaxies and then extrapolated the number of stars from that over there, and they've done the same thing over here and done the same thing over there, and they average those numbers out to account for the entire universe all around us, and they come up with a number that's so big that if we would have started our counting back then, a few minute or two ago, then we wouldn't even have hardly even started. In fact, it would take 30 million years to get to that number, counting at 10 billion per second. Now that sounds fantastic and almost unbelievable, and if you choose not to believe it, that's perfectly fine, because it's hard for me to believe as well. But as time goes on, there's just more and more galaxies found. In fact, when I first started these presentations, I guess it's been close to 15 years ago now, there was an enormous number of galaxies that they thought there were in the universe. And then they started using the Hubble Space Telescope and found out that they're underestimating the number of galaxies by a factor of 10 or 20. So 10 or 20 times more galaxies and that many more stars in the universe around us than what they were thinking just 10 or 15 years ago. Moving on, we'll take a look at a few more references to this stretching and spreading out. Isaiah 40 verse 22 says, "It is he that stretcheth out the heavens as a curtain and spreadeth them out as a tent to dwell in." Over here some more. "Thus saith God the Lord, he that created the heavens and stretched them out. I, even my hands, have stretched out the heavens, that stretcheth forth the heavens alone, who stretcheth out the heavens like a curtain." Over and over again, we're getting these references of a stretching or an expanding or a spreading. And there are some that have ETH endings, which gives the connotation of it happening currently. Some that have a past tense, showing that it happened in the past. And it's interesting that there was an astronomer by the name of George Lemaitre, I think, from Belgium, and an American astronomer by the name of Edwin Hubble, that together they were discovering that it appeared to be the universe was actually expanding and getting bigger, and the farther they looked out across the universe, those distant galaxies that were out there, the farther they looked through those distant galaxies, the more and the faster it appeared to be they were moving away from us. And so today, as they've studied more, the understanding is that they're moving away from us at a high rate of speed. In fact, they're moving away from us so fast out there at the far regions of the universe that we can't even hardly see them anymore, because it's basically a Doppler shift effect. There's so much space expanding between us and those galaxies, carrying those galaxies away from us, that light has a hard time getting back to us, even though it's moving at 186,000 miles per second. You've probably all come up to a train track and you heard a train coming toward you, and it has a high-pitched sound with its horn until it passes, and then the pitch lowers. Or maybe there's an airplane coming just above you. It's a higher pitch, and then it lowers as it passes. And that's because as these vehicles are moving away from us, the sound waves are stretched or rarefied, and so the pitch lowers. If these things were going away from us so fast that the sound couldn't hardly get back to us, then we couldn't hear them. Well, that's in effect what's happening with these galaxies far out there across the universe, and that's why they had to send up the James Webb Telescope recently, because they wanted to see some of those distant galaxies the light has been stretched so much that the wavelengths that we can see are stretched far into the red region, and our normal telescopes can't detect that. And so they send up a telescope that can detect those far infrared wavelengths and see those galaxies at the distant regions of the universe. So it's interesting to see how the Bible was describing this expansion. There's almost around a dozen references to this expansion in the Bible. And then we can move on and see some other things that the Bible has to say about astronomy. In Job 26:7, it says, "He hangeth the earth upon nothing." So we have this levitating earth. And this is contrary to what the ancients believed back at the time when this was written. For example, there were some that believed that the earth was carried on the back of a giant called Atlas. That's what the Greeks thought. And then the Hindus thought that the earth was carried on the back of 4 giant elephants. And of course, they needed to stand on something, so what better than a turtle? They thought the elephants were on a sea turtle, and the turtle was swimming in a giant ocean, so it's just, you have to keep putting something under the things that are holding up the other things. And it shows us how that if we reject God's ways and the things He says, then we only compound our problems, and the solutions have to be bigger and bigger, and each solution has to have another even bigger foundation. And there's, of course, no evidence for all these things. Now, the things that we've looked at so far have been that there was a beginning to the universe, and throughout history, unbelieving mankind, atheistic mankind didn't want to accept that, but the Bible has been saying, yes, that's the case. And there's also the case that the universe is expanding, whereas the ancients thought that the universe was static and unchanging and was not moving. They looked out and they saw the stars at the same place every night, and so they thought that this was one part of the universe that was basically they almost deified it, because it was a kind of almost like a form of a god, or a static and unchanging, immutable nature. But of course, today we know this is expanding. We can see that the universe, or the earth, is hanging on nothing, just like the Bible says, even though men longer ago thought that would be impossible. Another example is that the earth is round. It is He that sitteth upon the circle of the earth. And the original Greek here, it gives the connotation of round like a ball as opposed to round like a dinner plate. And then we have, of course, ancients. There were some in ancient history that thought the earth was flat. This here was written in Isaiah 300 years before the philosopher Aristotle first suggested that the earth might be round. And then there's Job 26, verse 10, where it says, "He drew a circular horizon on the face of the waters at the boundary of light and darkness." That boundary we call the terminator, and you can see it right here, the boundary between day and night, and you can see it's curved. It has this curved shape. The only way we would have a circular horizon or curved terminator right there, when we have an omnipresent or omnidirectional light source like the sun, is if that light source was projected onto a sphere. So in this verse here, it's just a given that the earth is round. It has a spherical shape. And of course, there's lots of other evidences in God's world that the earth is actually round, even though the flat earth theory has enjoyed a real resurgence in the last 5 to 8 years. The rotating earth is also mentioned here in Job chapter 38, verses 12 and 14. It says, "Hast thou commanded the morning since thy days, and caused the day spring to know its place?" Speaking about the earth here, it is turned as clay to the seal, and they stand as a garment. So the earth is turning once every 24 hours, and it's giving the appearance of the universe orbiting around the earth once every 24 hours. But of course, we know that's not the case. If it would be, if the universe would actually be orbiting around a stationary earth, then that would mean that the distant planet Pluto, which is almost 7,000 times closer to us than any of the stars, even though it's that close to us, it would need to go faster than the speed of light to get around the earth once in a 24-hour period. So here, again, we can see that the Bible is giving us another insight into the nature of the universe around us. And it's true. It's factually accurate, even though the Bible, admittedly, is not a scientific textbook. Here's another thing. At a time when about 5,000 stars could be counted in the night sky, the following statement was recorded in Jeremiah 33:22. It says, as the host of heaven cannot be numbered, neither the sand of the sea measured. So the Bible was saying that we actually can't count the stars. There's so many of them that we can't count them. Now, the Babylonians especially, and some of the Greeks, they were studious studiers or observers of the night sky, and I'm sure they had their numbers of stars, and I think I've actually read some of the ideas that they had of the number of stars in the sky. But the Bible was saying that, no, we can't count them. There's so many of them. Telescopes today show us that this is true. And the Bible was saying that as the stars of the heaven, and as the sand which is upon the seashore, and as the stars of the sky in multitude, and as the sand which is by the seashore innumerable. And it's interesting how it's comparing these two. It turns out that the modern estimates of the number of stars in the observable universe is comparable to the estimated number of grains of sand on all the beaches around all the continents today. So we can see there's an interesting correlation here with the Scripture again, with our understanding of how things are today. There's the matter and energy constant. This is the first law of thermodynamics. It's the most firmly established law in science. And it states that the total quantity of matter and energy in the universe is a constant. So we go through times when there's more matter in the universe, and that gets converted to energy. So matter decreases, but at the same time, energy increases because the matter is converted to energy. That happened when you drove your vehicle here this evening. You took matter out of the universe and you added some energy as you drove your car, and there was that process in the internal combustion engine. So the total quantity, though, never changes. The total quantity of the two is always the same. So there's no input, there's no output. And this is right, it goes right along with what we find in Genesis chapter 2, verses 1 and 2, where it says, thus the heavens and the earth were finished, and all the host of them. And on the seventh day, God ended his work which he had made. So this is a finished creation. There's no additional input. And that's borne out in the first law of thermodynamics. And then the second law of thermodynamics is the very well-established law that states that everything in the universe is deteriorating, running down, and tending to disorder. Now, there are pockets of order where things are flourishing, like here on the earth. But even here on the earth, we're also affected by the second law, or the law of entropy. And this is what the Bible has to say about it. Hebrews 1, 10 through 11 says, And thou, Lord, at the beginning hast laid the foundations of the earth, and the heavens are the works of thine hands. They shall perish, but thou remainest, and they all shall wax old as doth a garment. So the Bible is describing the second law here as well. And we also find that there's four primary, we describe the universe in terms of four things: that time, space, matter, and energy. And in the creation account, in the first paragraph of the creation account, if you want to call it that, in the first three verses, all of those are present: time, space, matter, and energy. And so we see all these ways that the Word of God is woven into the world that God has created, or the science that he has allowed us to study. And the interesting thing is that these things that we've looked at are things that were mostly contrary to what the ancients believed when they were written. The fact that the earth is round, that was something that lots of people didn't believe. The fact that the earth was spinning instead of being stationary, and the fact that the universe was expanding instead of being static, and the fact that the universe had a beginning, and some of these other laws that were mentioned, but they were written down as they were because the Spirit of God moved men to write them, and the Spirit of God is the Spirit of truth. And so we find truth in his word. Ecclesiastes 1:10 is where the preacher, as he called himself, was asking a question. Is there anything whereof it may be said, see, this is new? It hath been already of old time, which was before us. So these new descriptions of the way the universe works, or these modern day descriptions and discoveries, were actually written in the Word of God for thousands of years. Let all the earth fear the Lord. Let all the inhabitants of the world stand in awe of him. For he spake, and it was done. He commanded, and it stood fast. This is from Psalm 33, verse 8 and 9. And as we look at how God made the universe, if we look closely, we can see some amazing design elements that are there. And we might look at that closer later on, maybe Sunday morning, when we can see how that God created these things in such a way that it makes the earth here to be conducive to life. When God actually chose to put life here on the earth was ready, and it was finely tuned to make life possible. And it's such a tremendous, let me back up here a little bit. There's lots of parameters in the universe, lots of physical laws that could have differing positions or differing strengths, different forces in the universe that could have a wide range of strengths. And these parameters need to be set just right to make so that life can exist. And secular astronomers have been studying this recently. This is one of the forefronts of study these days as they discover how the universe is fine-tuned. It's called the anthropic principle. So we'll look at that later on. The heavens declare the glory of God, and we want to take a look at how these show a great creation, the things that we can look at, but an even greater God, a greater creator. We want to take a look at the structure of the universe, see how it's put together here in an orderly fashion. You can see the earth in the first cube, and the earth is a small part of our solar system. So you can see the inner planets here. This is the sun, represents the sun. This is the orbit of the first planet, Mercury. Out here is the orbit of Venus. Here's the earth, and it's about 93 million miles away from the sun. Then here's Mars, then much farther out is Jupiter and Saturn, Uranus, Neptune, Pluto, and the Kuiper Belt objects. So this here represents the solar system, but it should be 20 to 30 times bigger to include all the planets. But I'm constrained for space here, so this is not actual size, of course. The solar system is a small part of the Milky Way galaxy. Stars are arranged in groups like this called galaxies. And when you step outside at night here and you see that milky band of light stretching from, in midsummer, it goes from the northern to the southern horizon, you're actually looking at the combined light of all these stars. This is like a flat disk, kind of like a dinner plate. So when we look up in the summertime, we're looking along that flat disk, and we can see that concentrated band of stars. Then, of course, we see stars outside of that Milky Way region, too, and that's because there are stars above us and below us in the galaxy here. And so those are the stars that are real close to us. The milky band of light that we see, those are from stars much, much farther away from us. These galaxies are arranged into groups called clusters, and our cluster is called the local cluster. It has about 30 galaxies in it. And then as we leave our local cluster, we go across a void where there's really not much out there. And then we come to another cluster, and we have what's called the Virgo supercluster. That's what we're in, and our local cluster is a part of the Virgo supercluster. So a supercluster is a cluster of clusters. And so we have the supercluster we're a part of, then another part of the universe, we have another supercluster, and then out here's another supercluster, and they all come together to form some type of pattern that we can't really get outside of the universe and look in and see what it looks like. But as we look out through the universe, we get the impression that it has some type of a pattern like this here, a filamentary web of strings and voids of superclusters of galaxies spread all across the universe. And this is such an unfathomable scale here. We can come all the way down here to the galaxy, for example, this Milky Way galaxy. It looks like it's extremely dense, packed full of stars. And this is the place that we're in. We're about 2/3 of the way out from the center of the galaxy. And it looks like there's lots of stars there. And there is. And when we go outside at night, we can see those stars. But the nearest star to us is over 4 light years away from us, or 24 trillion miles. So we're in this highly populated region of space, and we're just a blip in the cluster. There's all that empty space, and then we have all this empty space, and then all the space between the superclusters, and there's just an incomprehensible size in the universe around us. And then as we go down into the microscopic world, we see lots of other design and order that mimics some of this design here. Like, for example, here we have the geometric shape of the Earth, and then there's the spiral pattern of these planets around the sun that mimics the electron cloud around the nucleus of an atom. We have the spiral design of the galaxies that's mirrored in some of the things on the Earth here, like ferns and other things, snail shells and things like that. So it kind of speaks of common design here. Not a lot of times when we see common design with things, there are some who say that it means that there's common ancestry, but that's not the case. It's just common design, a common designer. When we look at the size of these objects, we notice that they are far bigger than what we tend to think of when we see them at first glance. When we look at a star, they look like these tiny pinpoints of light that could be snuffed out by a blast of wind, kind of like a shimmering candle. And what you see on the screen now is an actual star, or 4 images of a star that have been slowed down 10 times. And you see these stars look like they're kind of twinkling. And this is a zoomed in, highly zoomed in view of one of the stars. I'll zoom in again and we'll replay it. This is what the stars look like through a powerful telescope. Most of the stars look like this. They're so far away that their light is coming from such a small speck that the atmosphere is distorting the image of the star, and the heat waves that are rising through the atmosphere is breaking up the image, causing the star to jump around and dim and brighten. And so that's what makes the stars twinkle. And if you notice, when you look at stars close to the horizon, they twinkle a lot more than the stars that are directly above. And that's because the stars down at the horizon are shining through much more atmosphere before they get to us, before the light gets to us. And so there's more of this twinkling effect. Some of the stars are big enough that they actually have a size that is measurable in our telescopes, an angular size, so then we can see really accurately how big they are. Betelgeuse is one of those, and we'll look at those later, that one later on. But now back to the Earth here. These are our local, this is in our local part of the celestial neighborhood here. The Earth is shown here. This is not a real picture, just a representation of it. This is Venus without the clouds. This is Mars, Mercury, and Pluto. These are the terrestrial planets, the ones that have solid surfaces. The others are called gas giants or ice giants, and they don't have solid surfaces. You can see the Earth is the largest of these planets. And then we have the Earth and the others circled now that we just looked at, and we've added Jupiter, Uranus, and Neptune. These 4 planets here are much bigger than the Earth. In fact, the Earth could be squeezed into Jupiter 1,000 times. So if you would pack Earths inside of Jupiter and you would take up all the empty space and cram Earths into that space, you could get over 1,000 of our planets inside this planet. So Jupiter is called the king planet. It's a big one. And then we have Jupiter and all the rest of them circled here at the bottom, here in front of the representation of the sun. The sun is big enough that you could fill it with 1,000 Jupiters or 1 million planet Earths before you'd fill the volume of it. If we were to take a jet and fly from the edge of the sun into the center, it would take about 30 days to complete that journey at 600 miles per hour. So flying a Delta jet in from the edge of the sun to the center would take about 30 days of nonstop flying. Moving on out, we'll go to Sirius, which is the brightest star in the night sky from our perspective here, and it's a good bit bigger than the sun. And there's Pollux, and there's Arcturus. Now we're getting up to giant stars. The sun is what's called a main sequence star, so it's a big one, but it's in the main sequence. That's where most stars lie. the main sequence and the dwarf stars. But there's other stars in the giant category that you see here. And Jupiter is just about 1 pixel in size there at the end of the arrow. The Earth is invisible at this scale. And then there's other stars that are even bigger than Arcturus, and we'll add those to the screen next. Here we have Arcturus and the Sun over here, and we've added Rigel, Aldebaran, Antares, and Betelgeuse. And Betelgeuse is so big that we could take this star and put it in our area of the solar system and replace the Sun with Betelgeuse, and this is what would happen. It would be so big that it would completely swallow the Earth's orbit and even extend millions of miles beyond the Earth and most likely swallow the orbit of Jupiter. And so as we look at this, we have Jupiter way out here, 5 astronomical units from the Sun, 5 times farther away from the Sun than what the Earth is. And so that means at night when we see Jupiter way up there in the sky, and we know that the Sun has set and it's just as far below us, 93 million miles away from us, just as far below us as it is above us during the daytime, if the Sun would expand to the size of Betelgeuse, it would get so big that it would swallow the Earth and extend millions of miles beyond us and swallow Mars and Jupiter way out there in the night sky. So this is an enormous star, and it's almost like God is creating these things just to show us who He is and who we are. It kind of puts us back into place. So these are in the category of supergiants. And these are the giant stars, and the Sun, again, is a main sequence. Where does this put us? I mean, you can't even see the Sun there anymore. Jupiter is 1,000 times smaller in volume than the Sun, and we're 1,000 times smaller in volume than Jupiter, our planet is, and then we're just like a flea on a speck of dust in this vast universe. There's another subcategory of the supergiants, and I'll bring one of them up in the background here, or a representation of it, and it's called VY Canis Majoris. It's about twice the diameter of Betelgeuse. Just huge. I mean, this thing is, how can we describe something like this? One thing for sure is it's bigger than any of our egos. It's just an enormous star that God has out there that is shining, bringing glory to Him, and declaring His nature, His powerful nature. How did God make these things? Psalm 33:6 says, by the word of the Lord were the heavens made, and all the host of them by the breath of His mouth. And so the answer is that He just spoke them into existence. Well, that kind of helps, but yet it doesn't. I mean, how can you just speak something into existence? When we think of making something, we think of getting pre-existing materials and a hammer and nail, or taking ingredients and putting them into a mixer and using beaters and putting them into an oven, and we assemble things from pre-existing material. But God made this from nothing, and the Bible says He just spoke them into existence. And that's just amazing. I mean, when I speak, I really don't get anything like this. I just have maybe some sound waves and a little spittle every once in a while maybe, but nothing like stars all across the universe. Now we see how big these stars are and how amazing they are. And this scripture here is just kind of like a caption for the image. This image looks almost like it could be a vapor cloud from someone's mouth on a cold winter day. So this here is a description of how God made these things. When God speaks, it's kind of like a release of energy. When we speak, it's actually energy happening, taking place. There's vibrations that happen, and so that's an energy release, and it travels across the room, and we can hear what each other are saying. When God speaks, there's much more of an effect that happens. It's interesting to see how that scientists have noticed that matter and energy are interchangeable. So if we release energy, we can convert it into matter so we can get solid stuff from that energy. Or we can take that matter and draw energy from it. Like I mentioned earlier, how we can put gas in the vehicle, that's matter. We can get energy from it. It's a forward motion of the vehicle. And we can also take a chunk of firewood, throw it in the fireplace, and we take the matter that was there, we convert it into energy. Then we have heat in the room. So that's one way that we get energy from matter. But in the beginning, God placed all that energy in the matter. So he released his energy and converted it into the matter that we have in the universe today. But how much energy did God actually put into all these things that we see? That's what's so amazing to me. When we do a matter to energy conversion, we do it in such an inefficient way. For example, when we put a chunk of firewood on the fire, most of the matter actually goes up in smoke or in vapor or stays behind in ash. And there's very little of it that's actually converted to energy. But in a nuclear reaction, there's a much more efficient transfer of matter to energy. And so it helps us understand more how much energy there is in matter. So nuclear physicists help us with this. And back in 1945, there was something that happened that helps us understand how much energy there is in matter. There was the bomb nicknamed Little Boy that was dropped on Hiroshima, Japan in 1945, I think it was. It was a terrible event. That atomic bomb exploded, and there were tens of thousands of lives that were lost from that one explosion, and almost every building in that city was leveled from that one explosion. And nuclear physicists tell us that in that bomb there was about 2.2 pounds of refined uranium that would have actually undergone a nuclear fission reaction. So that means that the uranium actually broke apart into smaller pieces. And when that happened, it released a lot of energy. So up there in the air where the bomb exploded, this uranium broke apart and was spread through the atmosphere. Now, if we could somehow gather up all those broken pieces of uranium and bring them back together in one place and put them on a scale, we would have less than 2.2 pounds because some of it was annihilated and converted to pure energy. So the matter ceased to exist and energy was liberated and came from it. But the amount of energy or matter that went missing is shockingly small. Only 0.9 grams, or about 1/30th of an ounce, is all that went missing, according to the physicists. So that's about one fingertip-sized pile of dust, about the weight of a paper clip. And that's all the matter that had to be annihilated in order to level the entire city. So how much energy did God put into the raw materials that make up your body? Or what about this nice big building and this planet that we live on? If it takes enough energy to destroy a city to make one fingertip-sized pile of dust. And then you'd recognize these enormous stars and how there's so many countless trillions of them all across the universe, and we're just astounded at the power of God. And it's no wonder that when God gives us some glimpses of his throne room in Revelation and a few other places in the Bible, that it actually talks about some of the energy that's taking place there, the temple shaking, lightning actually coming from the throne, almost as if there's energy pouring out from the throne of God and manifesting itself in the form of lightning. So to whom then will you liken God, or what likeness will you compare unto him? The stars are the most powerful natural objects that we know of, so if we were to compare God to anything around us, then the stars would actually be the closest thing that we could get to describing God's energy and his power. But these are only like vapor droplets from the mouth of God. He created them by his spoken word. So this is a star that's close to us. It's our sun. And I'll set it in motion here. And you can see some of the dynamic activity that's on the sun. This type of thing happens almost all the time on the surface of the sun. What you're seeing there are coronal loops. The sun has magnetic field lines. It's basically a giant bar magnet, just like the earth is. But the sun rotates at a differential rate. And so these field lines, sometimes they get twisted up enough that they pop out of the surface, and it carries that plasma out of the surface. They follow the lines, and then they plunge down into the surface of the sun again. So here we have lots of stars. Now that we see how powerful God, how our powerful Creator has created all these stars, how big they are, and then when we see a view of stars in our night sky like this, then it's really astounding. This is a cluster, two clusters of stars that you could see through a normal backyard telescope. So I'm kind of bringing this back home to us. something that's more accessible to us now with this image. This picture was taken through a 10-inch telescope there in Montezuma, and it's two clusters of stars. This one has blue stars, this one has yellow stars. It's interesting to see them juxtaposed against each other there, and it's just lots of stars all in one view. And this covers an area about the size of a thumbnail held at arm's length. So you can see a lot more stars through a telescope that you can't see with the naked eye. Now what I'd like to do is take a look at one other spot in the night sky that you can see in November, right after sunset, when you look straight up. That's how it is there farther south. Now here, farther north, you have the sky getting darker earlier than what we do down in the south. So it might not be straight up for you here. But late fall, generally, this galaxy is about directly above us, right after sunset. And you could blot it out with a thumb held at arm's length. To us, it looks like just a dim haze, a dim glow, but in reality, it's a big patch of stars called the Andromeda Galaxy. And I want to show you what it looks like here. A close-up view of this. We've got some audio going, but I guess it's kind of low. So I'll just keep talking here while this is playing. So this is what happened here is that we took about a quarter-size section of the Andromeda Galaxy, and we're using some Hubble Space Telescope imagery to zoom in on this quarter-size section of the Andromeda Galaxy. And as we're zooming in here, we're coming up to the outskirts of it, the outer regions, and you can see how we're starting to resolve into lots of individual stars here. And these stars, as they are, we'll start panning through, and it'll take us all the way up to the center of the galaxy. And this is the Andromeda Galaxy. It's the nearest major galaxy to our galaxy. It's about 2.4 million light years away. So with our normal telescopes here on the Earth, like my telescope at home, I can't resolve these individual stars, but we need a powerful telescope out there in space above the distorting effects of the atmosphere to actually resolve these millions and billions of stars in the Andromeda Galaxy. Now, I'm playing this now after we see how big the stars actually are. The stars are, like I mentioned earlier, they're enormous. They're far bigger than anything we can comprehend. And in this view here, you see one after the other, just so many of them panning through the view here. As we come in closer to the center of the galaxy, we can see some of the dust, cosmic dust scattered through here. That's the darker areas, the reddish areas. And then we have brighter patches. That's not necessarily areas with more stars. It's just areas where the cosmic dust doesn't block the view of the background stars. But now, as we get closer to the center, we have stars that are so close to each other that we're losing the capability of distinguishing one star from the other. And it's just so many of them that they all appear as one solid glow. And then you can see the cosmic dust fingers stretching out through it. So this one galaxy next to us, the nearest major galaxy to ours, has this astounding level of stars. Now that we're close to the center of it, we just see this vast sea of stars. Now, they're not so close to each other that they're actually touching like it looks like in this image. It's just that the optics on the telescopes that we use don't have the ability to finally resolve these stars into pinpoint images like they really should be. So they're kind of bloated compared to what they are in actuality. As we shrink back out here, we can see how that we were looking at just a small section of the Andromeda Galaxy. We were exploring some of the stars in that region, and this Andromeda Galaxy is just a small part of our night sky. And there's literally billions more galaxies all across the universe. So it's another reminder of who our God is and his creative power, and that he can make these things with his spoken word. Next, we'll take a look at the size of the universe, the distance of these objects from us, and of course, I want to say up front, these are estimates, but astronomers have a pretty good idea of how far these objects are from us, especially the nearby objects like the moon, 238,000 miles away from us. And of course, this is only at certain times of its orbit. The moon has a somewhat elliptical orbit, so sometimes it's farther away from us, sometimes it's closer. But they can get a good average measurement. They actually left a reflector dish on the moon. It's a mirror up there, and it was left there by the Apollo astronauts. Now today, here on the Earth, we can shine a laser beam up to the moon and time the amount of time that it takes for the laser to be reflected back to the Earth, and we can see how far the moon is from us. And it turns out that it's actually moving away from the Earth at about the rate of the speed that your fingernails grow. And it's about 1.5 inches a year or so that this moon is moving away from the Earth. And that's not because God put it in its orbit at the wrong orbital speed, but it's simply that the moon is drawing energy from the Earth, stealing energy from the Earth because of the tides washing over the Earth. That energy is being transferred to the moon, making the moon's orbit enlarge, while the Earth's rotation speed is actually slowing. So it's kind of like a wireless transfer of energy. So the moon is close to us. It's about 20 days away from us at 600 miles per hour. And then the sun is about 93 million miles away from us, about 400 times farther than the moon. And it's actually about 400 times bigger in diameter, too. So for that reason, they look like they have exactly the same size in the sky. So I think it's more than a coincidence, because what that does is it makes so that we are the only place in the whole solar system of all the other worlds out there, the other planets, and all the dozens of other moons. None of the other worlds in our solar system give us a view of a total solar eclipse like we have here on the Earth. Then moving on out to the edge of our solar system, 3.7 billion miles away, we come to Pluto, the dwarf planet. It's about 700 years by airliner, or moving at 600 miles per hour. And traveling at 65 miles per hour, it would take about 6,500 years to reach Pluto, which is 40 times farther from the sun than what the Earth is. Now the next step we'll take is going to the nearest star aside from the sun. It's 4.2 light years away. This is Proxima Centauri. And if we convert this back into miles, it would be 24,689,719,000,000 miles. It would be about 6,800 times farther than Pluto, and a 4.7 million year flight. And so you can see how we've taken a giant leap just to get to the nearest star, and you probably also noticed how that we used a different unit of measurement. And these units of measurement, like light years and parsecs and megaparsecs and astronomical units, they're really confusing for us. It's hard for us to understand. But it's important to use them because the distances get so big that the numbers, if they're used in miles, become meaningless. So it's kind of like astronomers use light years for the same reason that we use miles to describe how far we got here this evening instead of using inches. We wouldn't say we had to drive 1,762,000 inches to get here. It just wouldn't make sense. So astronomers use light years, and that's what I'll use to describe some of the other distances. So we'll move to light year, I'll give you an explanation for a light year if you haven't realized it already. Probably a lot of you do. A light year is the distance that light travels in 1 year. And so it moves at 186,000 miles per second. That's fast enough to go around the Earth 7 times in 1 second. And that's faster than we can get to church on Sunday morning. It's really moving. Now, if we let this light go for 1 year and go out in a straight direction away from us for 1 year, we get up to the distance of about 5.88 trillion miles. And so you could round that off to 6 trillion miles. So 1 light year is approximately 6 trillion miles long. Now, another thing we can do to help us understand these numbers, like 6 trillion, is we can take a look at a scale here from 1 to 1 billion. And as we leave 1, we have to go through the number groups like the tens, and then the hundreds, then the thousands, and then the millions before we get to 1 billion. So where should 1 million appear on this scale? A lot of times we tend to think it's about half as big as a billion, but of course, maybe when we're younger we think that way. But in reality, a million is much smaller than 1 billion, and the proper location for 1 million on this scale would be 1/10 of the way to the next dot after we leave 1, and we have this entire distance to cover before we get to 1 billion. So I have 100 dots on here, so if you want to check me, you can, you have what you need to know to see if this is accurate. And then on the scale from 1 to 1 trillion, we have to squeeze in the tens, hundreds, thousands, millions, and the billions before we get to 1 trillion. So we have to have 1 million and 1 billion in here before 1 trillion. So where would we place 1 billion? It's actually the same way down here, 1/10 of the way to the first dot after we leave 1. That means we have the entire top scale squeezed into the tiny space between 1 and a billion, and we have all this distance to cover before we get to 1 trillion. And 1 light year is, again, 6 trillion miles long. So the reason I'm showing you this is that we have to understand these numbers in order to be able to understand the universe that the numbers are describing. So maybe one more illustration. Here we'll take a familiar object, at least maybe to some of you out there, a $100 bill, and we'll add to this and we'll see how much area $100 occupies. Or excuse me, $1 trillion occupies. So what we'll do is we'll have a stack of it about an inch high, and that equals $10,000, as you see here. And then another stack of $1 million. And these are all $100 bill increments or denominations. We're not using 5s, 10s, or 20s. There's 100 million. Here's $1 billion. And we would need 10 pallets to hold this much cash. And this is why you never hear of a bank being robbed of $1 billion. It's just too much work. It would take a semi-truck and a forklift to take off with the haul here. So this is $1 billion represented by $100 bills. And the next and final step, we'll just go ahead and jump up to $1 trillion, and that's what you see right here. And you can hardly see our midget for comparison over here. But one thing you can see is a dark line running through the center here, and that's the second row of pallets. So these are stacked too high, and we still need all this area to hold $1 trillion in $100 bills. 1 light year, again, is 6 trillion miles long. Okay, now that we understand 1 light year, let's move on out farther into space. And we have the sun between 2 spiral arms, about 2/3 of the way out from the center of the galaxy. This galaxy is huge. The stars that we see in the night sky, the individual stars, are mostly all contained within this yellow circle. So we're only seeing a small part of what God has actually made as far as stars within our own galaxy. But the entire galaxy itself stretches almost 100,000 light years from one end to the other and contains over 100 billion stars, astronomers believe. And then, as we look farther out, we can come to the Andromeda galaxy that we looked at earlier in detail. That's 2.4 million light years away from us, or if we would convert this into miles, it would be 14 quintillion, 108 quadrillion, 411 trillion, 189 billion, 256 million miles away from us. And of course, this changes over time. These galaxies are orbiting around out there and things like that, and we can't get just super precise measurements. But converting this number into miles would give you that, and it helps us understand why astronomers don't use miles to describe distances, because we're just at our next door neighbor here, and we have enormous distances like this. So as astronomers had been looking into the universe, they were looking out 5,000 times farther at other galaxies, but of course they keep building bigger telescopes and looking even farther. If the sun were a large grapefruit here, the Earth would be smaller than the head of a pin and about 50 feet from the grapefruit sun. So it kind of gives you a sense of scale for our local solar system here. And at this scale, Proxima Centauri would be about the size of a cherry over 2,000 miles away. So that would put the nearest star close to the east coast out there if the sun and the earth were 50 feet apart from each other right here in this building. So there's lots of empty space in space, which is probably why they call it space. Isaiah 40, verse 12 says, "Who hath meted out heaven with a span?" Now for me, when I look at these things, I definitely feel spaced out. But when I see how the Bible talks about how that God is so much greater than all these things he's created, and it gives us the word picture here of him just measuring out the universe with a span. A span is the width of a man's hand from the end of the little finger to the end of the thumb. And it's giving us a word picture here of the Creator just measuring out the universe with a span. And of course, this isn't telling us that God has a physical size that's this much bigger than his universe. He is a spiritual entity, but it does give us an analogy to help us understand his greatness above all that he's created. There's another picture that I want to show you here. It's coming up. It's the next one we'll look at. And it's one of my favorite pictures in all of astronomy, and it's not because of any type of beauty or aesthetics that you see there necessarily, but it's because of what it tells us and what it shows us about the nature of the cosmos around us. And it was called the Hubble Ultra Deep Field Photograph, and astronomers had their shiny new telescope out there in space that could do some unprecedented things, and so they were wanting to really try it out and see what it could do in looking far out across the universe. So they tried to find a spot in our night sky that had basically nothing in it from what we could see here with our small telescopes. And they found a spot like that right here in the center of this image. I think it was between these three stars right here where they found a dark hole out through our galaxy. And so they wanted to look at that and see what was there. So they pointed the Hubble Space Telescope at that region. They zoomed in on it, and they opened the shutter on the telescope camera for a total of 11.3 days while they were looking at this tiny speck way out there in the universe, and the photons of those distant galaxies trickled in on the sensors. And after that exposure time was finished, they processed it into this picture here. Almost every dot, smudge, and speckle of light that you see on the screen now is not just a star, but it's an entire galaxy of millions and billions of stars. And the surprising thing is that it covers an area of sky so small that if you were to go outside at night and reach down and pick up a coarse grain of sand and hold it at arm's length, it would completely blot out this entire field of galaxies. So astronomers have counted 10,000 galaxies on this one image. You can't see them all here on the screen right now, of course, but there's 10,000 galaxies here that you could hide behind a grain of sand at arm's length. And a grain of sand at arm's length is about the same angular diameter of the glare of light from one of the brighter stars in the night sky. So the next time you go outside and look at one of those brighter stars, just think of it, how that behind the glare of light from that star, there's probably a whole field of 10,000 galaxies with millions and billions more stars in that tiny little space. Moving on. Measurements showed that the most distant galaxies observed to date are about 12 billion to 16 billion light years from the Earth, and they are observed in every direction across the sky. Regardless of where we look, there's just galaxies everywhere. And I don't think the end of the universe will ever be found. And this is just a personal opinion, so it's hardly worth putting up here on the screen. But I base that on Jeremiah 31:37, where it says, "Thus saith the Lord, if heaven above can be measured, and the foundations of the earth searched out beneath, I will also cast off all the seed of Israel for all that they have done, saith the Lord." Now we know that there's no way we could dig to the center of the earth and discover the metaphorical foundations of it there. And there's also really no way we can find the ends of the universe and lay a yardstick across them to see how big the universe actually is. And I don't think it will happen because the Lord has not cast off the seed of Israel, but since this was written, he has made a way for Israel to be saved. So the price has been paid and the redemption has been given, and so Israel has not been cast off. So I don't think we'll ever find anything that we could call the end of the universe. Psalm 8, verse 1 says, O Lord, our Lord, how excellent is thy name in all the earth, who has set thy glory above the heavens. So all these things that we've seen this evening they carry a particular glory, and it's amazing to see. It's fascinating. But these things are just like a reflection of their Creator, and the Creator himself, his glory is high above all that we see in the heavens around us. All right, I think we will leave it at that for now, but I will have a time for questions here in just a minute. So if you would like, if any of you have any questions about what we talked about this evening, feel free to ask those in just a few minutes or in a minute or two. But what I have on the screen now is a representation of astronomical event cards from a couple years ago. I haven't updated these pictures yet, but I have updated cards in the back on the table over here. So if you would like to have some, help yourself. I have more than enough for one per family, so help yourself. These are astronomical events for 2022. So we have meteor shower dates on here, conjunctions of the planets, any significant events in the night sky will be on there. There's an upcoming lunar eclipse, so you'll want to be sure to check that out. And then it's just a few scriptures or a write-up on the front. So I think that's about all I have. Now it's your turn. Do you have any questions? How do we know what the shape of the Milky Way is? A good question. So basically what's happening is astronomers are looking at stars out there around us, and they're getting the distances for those stars. And as they look above the galactic plane, they come to a certain point and there's no more stars. It's just not many out there. The redshift and or maybe I should say the parallax measurements show that the stars only go to a limited distance as we go above and below the galactic plane. But as we look into the galactic plane, into that Milky Way band above us, and then on the other side all around us, we get measurements for stars that are much, much farther away, and they extend way out. So it shows us that these are all arranged into this flat disk. But yes, like you mentioned, we can't actually come outside of it and take a picture of it and see exactly what it looks like. But another thing that we can do is we can take pictures of other galaxies out around us, and we can especially notice the ones that have a lot of the same characteristics as our Milky Way galaxy does. And those actually, we see them exhibiting a spiral shape like we think the Milky Way has. Some of them are face on toward us, others are edge on. And so that's another way that we can get a good idea of what the Milky Way is like. Anyone else?
The idea of the expanding universe, how old is that theory? Who first discovered that?
Sure. That dates back to the early 1900s. The 1920s, 1930s is when they first started seeing that it looks like the universe is actually expanding. And the reason they discovered that is because they were looking at galaxies far out of the universe, and they discovered that they were extremely redshifted. And that redshift shows that they're moving away from us faster than other galaxies that are closer to us. So it's not necessarily that the galaxies are on a trip away from us, but it's just that space between us and the galaxies are expanding and is carrying those galaxies with. So it's kind of like a loaf of bread that's rising. We could think of a loaf of raisin bread. You have a lot of raisins in the bread, and the raisins can represent the galaxies. As the bread rises, the raisins move apart from each other. And that's what's happening with these galaxies. They're moving apart from each other. Now, on a local scale, galaxies that are close to us, some of them have a high enough speed that their kinetic energy is causing them, as they orbit, they might actually be moving toward us, overcoming the expansion of space between us and that galaxy. But the distant galaxies, they're so far away from us that there's no way they can move toward us fast enough to overcome that expansion of the universe. And so they are moving away from us, and they're all redshifted. the amount of expansion in the universe, just for perspective, I showed you our nearest major galaxy, the Andromeda Galaxy. The amount of expansion between us and that galaxy is somewhere around 30 miles per second expansion of the universe. That much space is expanding between us and that galaxy, if I remember right. So that gives you an idea of how much is expanding between us and that nearby galaxy. And then if you go to the other end of the universe, you can see it would be a much greater speed. Anyone else? Good point. It is. It's actually inverted from what it is. So let's see, right now, if you look at the Big Dipper is just sitting there real nice, like one of our wives just set it on the counter or something. It's sitting there holding liquid, or if you could imagine that way. So it's kind of sitting on the horizon for us down in Georgia. But I noticed here, up here in this part of Montana, it's about 15 to 20 degrees above the horizon. And 6 months from now, if you would go outside at the same time of the night, it would be upside down and above the North Star. Or if you just want to go out in the morning, 6 or 12 hours after you saw it in the evening, you would see it having that same upside down orientation, because the Big Dipper makes a complete circle around the North Star once per day. But there's a precession throughout the year, so if you go out the same time each night through the year, you'll see that the Big Dipper has moved a little more clockwise every night, or counterclockwise. Anyone else? Yes. Yeah. Right. So it's nobody home. That's a good description in one way, but another good description is it's everybody home, and that's why it's a black hole, because there's so much stuff there. That's not what I was referring to on that picture. So I'm glad you brought that up, because sometimes there has been that misunderstanding. It wasn't a black hole according to the technical definition of a black hole. It was just a dark area in our galaxy. So basically, nothing there, no cosmic dust to get in the way, not a bunch of stars there. We could just look far out into the deep regions of the universe. A black hole, the technical understanding, or the actual term black hole, refers to something else that hopefully we'll get a chance to look at later on. Thank you. Anyone else? I think someone else raised their hand. Yeah. Right? Sure, I can do that. Let's see. It will make it easier if I actually bring up a slide here, and I'll see if I can get this thing to work. Here we go. We'll come down here. I've got a few slides that could help explain that. So a redshift, again, is it can be compared to the Doppler shift. I don't have a real good connection with my computer up there. It can be compared to the Doppler shift with sound. Here we go. And we'll come up here. Here's an example of redshift on a nearby planet. So this is Jupiter. Jupiter's in our solar system. Jupiter is actually turning. So this side, the right side of Jupiter, is approaching us. The left side is receding away from us. So if we take a segment of light here and we split it into the spectrum, all the different colors that you see here, there's actually absorption lines here that are they're basically missing light. The reason there's missing light there is because Jupiter has certain elements here, hydrogen and helium, that absorb some of the light. Jupiter keeps some of the light, sends the rest of the light our way. So when we get the light here and we split it with a prism, then we have these dark lines. So this is an actual, the electromagnetic spectrum of Jupiter. And if you see here, these lines don't really run straight across. They're slanted up on the right side. And the right side here of the spectrum corresponds to the right side of Jupiter, which is approaching us. So those lines are pushed up into the blue end of the spectrum. And on the left side, where the planet is receding from us, those are pushed down into the red side of the spectrum. So you see here how this line is slanted down toward the red because it corresponds to the side of the planet that's moving away from us. So this is one simple illustration of it. Light, as it moves away from us, there's almost like a Doppler effect. Whereas with sound, we can hear the pitch lowering as the object moves away from us. With light, when we look at the absorption lines, they actually get pushed down into the red end of the spectrum. So as we look at galaxies far out across the universe, they're moving away from us so fast that their light is buried way down here in the red so far that I, for example, wouldn't even be able to see it with my telescope, because my telescope is looking at this region of light here where all the colors are. But those galaxies, the only part of light that's left coming to us is way down in the infrared part of the spectrum, which is the part of the electromagnetic spectrum that carries heat. So when you feel the sun shine warm on your hand, then you're actually feeling infrared radiation. So that's why the James Webb Telescope has to feel the heat from those galaxies instead of looking at them. And that's why they have to have the telescope the temperature dropped all the way down to less than 400 degrees below 0 Fahrenheit. It's extremely cold on that telescope. And the reason for that is to make so that there's no heat, excess heat radiating in onto the sensor, because if there would be 200 degrees below 0 heat flooding the sensor, they couldn't see those galaxies way across the universe because there would be too much noise there. Does that help explain? Hopefully so. Okay. All right. I think there was someone else? Okay, sure. Yeah. Right. So thank you for that, Wendell. We have about 3,000 stars that we can see generally on one night today. I mean, we don't see quite as many because of light pollution and that kind of thing, but about 3,000 stars for half of the night sky or half of the dome, and then, of course, on the other side there would be another 3,000. Those are stars that are above magnitude 6, or actually below, depending on how you referred to it, but brighter than magnitude 6. Magnitude 6 is about the limit of naked eye visibility. And there's about 3,000 stars that are brighter than magnitude 6 on any given night. So approximately that many. Now, of course, when we go out at night and we see all those stars, it looks like it's much more than that. Part of the reason for that is because the stars, you see the bright ones, then you see dimmer ones that get dimmer and dimmer and dimmer to where they eventually just kind of, they morph into the background glow of stars. And so it's hard to distinguish that, and it gives us the impression that there's a lot more out there than just 3,000, which is an accurate impression. Good point. They, in a way, they do that we can't hear. For example, the sun, in one way, the sun is a thermonuclear bomb in the sky. So it's continuously exploding, giving a tremendous amount of energy. We can't feel the shock waves or hear the sound because there's no medium in interstellar space or in the solar system here to carry that to us. So we can't hear the sun. If there was atmosphere between here and there, then maybe we could hear it. I don't know if sound probably would be all absorbed by that atmosphere between here and there, of course. If there was that much atmosphere, it would probably collapse into a black hole because of all the mass. But so technically, the sun has a gigantic roar up there, but we don't hear it. There's nothing to carry the sound to us. But what we can do is listen to the sun, just like we listen to Wendell or Tom on the phone. We can tune into the sun with radio waves or other stars, and we can hear through that. And so we actually get a message. There are astronomers that they've built lots of radio telescopes all over the earth, and even some extremely large telescopes. One is in West Bank, or the Green Bank Observatory in West Virginia. It's the largest machine on wheels on planet Earth. It weighs 17 million pounds, and it has over 1 million pounds on each wheel. And one of the biggest engineering challenges of the telescope was to create a track system that could carry the weight of that telescope without just breaking the iron tracks. And they keep having iron tracks that are broken by it. But anyway, this telescope has a collector dish that's over 2 acres in size. And so it's listening in on stars way out across the universe and distant galaxies out there as well. So that's another way that we can perceive things around us. And another thing that we can do for the first time ever is actually feel the distant universe. Einstein proposed that there would be a way that there would be something called gravity waves permeating the universe as a result of things like black hole mergers as they spin around each other. Just before they merge, it's kind of like 2 jet skis on a lake going around each other, sending out waves. So he said that if we have a space-time, then as these stars orbit around each other at a high rate of speed, then they would send out ripples through space-time, and as those ripples pass across the Earth, then we would get jostled here on the Earth. So they built these, just a few years ago, they built these LIGO observatories. One is over here in Oregon, the other is down in Louisiana. And what they have is these long arms that are more than 1 mile in length, and they have lasers shining through the arms, and they detect when there's an elongation of the arms. And they have detected black hole mergers and neutron star collisions and things like that by simply feeling the universe shaking as a result. So it's an amazing new window into the universe. Not only are we seeing and hearing, but now we can also feel those things. Okay, I think it's about 9 o'clock now, so save your questions for tomorrow night. I would really enjoy the Q&A time, so if you have any questions now, don't just forget them, but save them for tomorrow night. And I think that's all we have for now. Don't forget to pick up some cards on the way out, and thank you for your attention.